Okay, so we are going to start the program. So first of all, on behalf of the Early Career Hydrogeologists Network, I would like to welcome you all for joining this webinar. And first, I would like to thanks to the Professor Kei for accepting our invitation and agreed to give a lecture on the very concerning issue on groundwater nitrate nitrogen pollution. Thank you so much, Professor Kei, for agreeing to give the lecture for Early Career Hydrogeologists Network, ECHN. And I would like to just little bit brief about the Early Career Hydrogeologists Network. It's an official network of the International Association of Hydrogeologists, we generally call IAH, to providing the forum for the young researchers at their early career stage to learn more about the hydrogeologists, develop their network and career opportunities in the field of the hydrogeology. So we have total 12 chapters and we have working group as well. In there we have committee, each and early career committees. We are members from different regions to work whole year to engage our early careers researchers, especially working in groundwater and hydrogeology, to have networking, collaboration, and learning. So on behalf of the ECHN IH, I would like to welcome you all once again. And before to start the session, I would like to just introduce the speaker of the event, Professor Kei Nakagawa. Probably I have pronounced correctly, Professor. Is this correct?
Yes.
Thank you so much. So he's a professor in the field of environmental groundwater science and has more than 30-year teaching and research experience in this field. Currently, Professor is working as a full professor of the Graduate School of Fisheries and Environmental Sciences of Nagasaki University since 2011. And his research areas are groundwater contamination, modeling, seawater intrusion, and also he's working on remediation of contaminated soil and groundwater. So last 2 decades, professor is working on nitrogen and nitrate pollution in groundwater in different part of the Japan. And today's lecture is going to focus on the groundwater nitrogen nitrate pollution in Shimabara, Peninsula, Japan. So without any further delay, I would like to invite you, Professor, to share your experience with us. Thank you, Professor.
Okay, thank you very much. I'm Kei
Nakagawa. I would like to just say, if the participant have any question, please write on the chat box. We will take the question in the last, and we will have discussion. Thank you so much. Professor, please.
Okay. I'm Kei Nakagawa, professor of the Institute of Integrated Science and Technology at Nagasaki University. Today, I'm going to present our research initiatives on groundwater nitrate nitrogen pollution in Shimabara Peninsula, Japan, which is a crucial issue for local water security and environmental health. Okay. To begin with, I would like to briefly introduce my background and the scope of my research. I received my PhD in engineering from Kyushu University in 1999. After that, I worked at Kyushu University as an assistant professor, then at Kagoshima University an associate professor. And since 2011, I have been a professor at Nagasaki University. I also had an opportunity to work as a visiting researcher and a visiting professor at Lund University in Sweden. During my student years, my research mainly focused on numerical modeling, especially seawater intrusion and high-level radioactive waste disposal in deep underground. After joining academia, I started working on laboratory experiments and numerical modeling for soil remediation. including phyte remediation and electrokinetic remediation of heavy metal contaminated soils. I have also worked on water and solute transport in heterogeneous soils and on the optimal design of subsurface cutoff wall to prevent seawater intrusion in coastal aquifers. At Nagasaki University, I have been working on various aspects of nitrate contamination in groundwater, which is the main topic of today's talk. This includes field investigations as well as analysis of groundwater, river water, and soils, statistical modeling, and numerical simulations. At the same time, our laboratory currently conducting a wide range of research projects, including pollution source identification using sterols, optimal groundwater resource allocation under climate change, PFAS distribution in marine sediments, and GCM climate data downscaling in New Zealand. So overall, my research combines groundwater flow reactive transport modeling and geochemistry, which allows us to approach the complex groundwater problems from multiple perspectives. First, please take a look at the figure on the left. This is the well-known planetary boundaries framework proposed by the Stockholm Resilience Center. Looking at the global scale, the nitrogen cycle has already exceeded the Earth's limit and is in a state of failure, adversely affecting water resources around the world. This nitrogen issue is not exception in Japan. In Shimabara city, nitrate concentrations in public water supply wells have shown a continuous upward trend over the past 50 years. Since the region relies entirely on groundwater for the drinking water supply, the fact that many wells are approaching or exceeding the 10 milligram per liter standard poses a direct threat to the community. Here, I would like to present a series of studies that have been developed based on our research on nitrate contamination in Shimabara Peninsula. I joined Nagasaki University in April 2011, and we started field observations and water quality analysis shortly after in August of the same year. However, the first significant results began to emerge around 2015 or 2016, so it takes 5 or 6 years. We first reported the status of nitrate contamination in Shimabara city in environmental earth sciences, including statistical analysis. We then expanded our study area to Unzen city and Minami Shimabara city, and published a series of papers based on these results. Alongside these field observations, we evaluated nitrogen input. Alongside these field observations, we evaluated the nitrogen input using a statistical open data and found that it corresponds well with the increasing trend of nitrate concentration in groundwater. This is from the statistical data. This is the nitrogen concentration in groundwater. So this result clearly indicates that reducing nitrogen input is directly linked to mitigating contamination. This nitrogen input can be regarded as nitrogen loading potential, and its major components are considered to be domestic wastewater, chemical fertilizers, and livestock waste. To distinguish which of these sources contributes most to the contamination, we proposed a new method using coprostanol concentration, which is produced by the reduction of cholesterol in the intestines of animals, in gut of animals. However, we found that the detection levels of coprostanol differed significantly between the river water and groundwater. To investigate this, we examined its adsorption behavior in soils and sediments. In parallel, to further utilize open data, we applied the LMDI method for factor decomposition to clarify changes and contributing factors of nitrogen input. In the Shimabara Peninsula, livestock waste showed a particularly high contribution to the nitrogen loading potential, since heavy metals are often added to livestock feed for growth promotion. So we hypothesized that co-contamination of nitrate and heavy metals may occur. Based on this idea, we investigated the concentrations of heavy metals in the soils in Shimabara City and later expanded the study to the other regions in Japan. Carrot is one of the major agricultural products in Shimabara City. Therefore, we also conducted experiments to examine whether adding biochar to contaminated soils could control the transfer of heavy metals to crops. Finally, in parallel with these studies, we have developed numerical simulation models to reproduce the historical spread of groundwater contamination, as well as to evaluate the effectiveness of different source control measures through scenario-based simulations. Okay, so our 2025 study provides a comprehensive overview of the current conditions across the entire Shimabara Peninsula. In this section, I will present our findings on water quality classification and spatial distribution. The peninsula consists of 3 cities, Shimabara City, Unzen City, and Minami Shimabara City, 3 cities. The trilinear diagram on the left indicates that the samples from all 3 cities are affected by pollution, because the panel 3 is plotting the samples on the panel 3 is the samples are affected by the nitrate pollutions. With Shimabara City showing the most pronounced impact. Red colored the triangle shows the samples from the Shimabara City. Using hierarchical cluster analysis, we classified the water samples into 5 clusters. In the hexa diagram, this top right figures, the black-shaped 2 positions section represents nitrate ions. So cluster 3 is clearly the group most affected by nitrate pollution and is predominantly distributed in northern Shimabara City. These gray-colored symbols are nitrate-affected samples. Using the water quality evolution diagram on the left, we assessed whether the aquifers are undergoing seawater intrusion or recovery. We confirmed that cluster 4, yellow one, located at the southern end of peninsula, is in a recovery phase. On the right, the nitrate concentration map shows elevated levels in agricultural areas. Importantly, nitrate runoff from the northeastern part of the peninsula contribute to nutrient enrichment in the Isahaya Bay Reclamation Reservoir. Actually, here is a reclamation area, and here is the pond to the water used for the agricultural activities in the reclamated area. This highlights the importance of groundwater management for protecting the surrounding coastal ecosystem. Okay, these are the background of the studies. So to investigate the causes of such groundwater contamination, we have considered measuring coprostanol concentrations. Here we present a case study of rivers in Shimabara city. I'm sorry, this is not the groundwater, but the river water studies. Until now, to identify the source of nitrate nitrogen pollution, isotope ratio analysis has been widely used. This method plot nitrogen isotope ratios on the horizontal axis and the oxygen isotope ratios on the vertical axis to infer pollution sources. However, data points often overlap in the regions associated with the livestock manures and chemical fertilizers, making it difficult to identify the dominant source of pollution. So to address this issue, we have investigated a method using a coprostanol concentration to determine whether the pollution originates from livestock manure. Coprostanol is an indicator of fecal contamination produced by the reduction of cholesterol in the intestines of animals, such as livestock. It is also known that under natural environmental conditions, cholesterol can be further reduced to cholestanol. This is prostanol. This is a cholestanol, the different chemicals. Therefore, we propose identifying the primary pollution sources by analyzing coprostanol concentrations together with the sterol ratio, defined as coprostanol concentration divided by the sum of the coprostanol and cholestanol concentrations. So regarding the sampling locations and measured parameters, we collected water samples from 42 sites across 15 rivers in Shimabara city over a 3-day period. Field measurements included pH, electrical conductivity, oxidation reduction potential, and bicarbonate concentration determined by titration. In the laboratory, we analyzed the samples for major ions, coprostanol and cholestanol. This map shows the distribution of coprostanol concentrations using the previously proposed guideline values of 700 nanogram per liter for drinking water and 500 nanogram per liter for surface water as reference threshold. The areas marked in yellow, orange, and red indicate relatively high coprostanol concentrations. In particular, elevated concentrations observed in the upper reaches of the Nishi River, this river, suggesting that this area is affected by fecal contamination. On the other hand, the distribution of sterol ratios defined as coprostanol concentrations divided by the sum of the coprostanol and the cholestanol concentrations, shows that locations exceeding 0.5 are clear indicator of contamination, marked in red. This indicates that in addition to the upper reaches of Nishi River, the upper reaches of Yue River, another river is here, are also affected by fecal contamination. When locations with sterol ratios of 0.3 or higher are considered, the orange marked sites are also included. This suggests that many locations are likely influenced by livestock waste and domestic wastewater. The distribution of nitrate nitrogen concentrations is shown on the left for surface water and on the right for groundwater. High concentration areas are consistently observed in the northern part of Shimabara city, where extensive farmland surrounds the Yue and Nishi rivers. By comparing these results with the sterol ratio analysis, sites exhibiting both high nitrate nitrogen concentrations and high sterol ratios are considered to be influenced by livestock manure. For more detailed identification of the primary pollution sources, please refer to our original paper. And next, I would like to introduce a method for decomposing the factor contributing to groundwater nitrate nitrogen pollution. We propose an approach to analyze the factors responsible for increases or decreases in nitrogen input over arbitrary time intervals. This is the proposed analytical framework. Nitrogen supply is defined as consisting three sectors: crop production, agricultural crop production sector, livestock, farm animals sector, and household sectors. Each sector is further characterized by factors such as intensity, structural composition, and scale changes. Here, as an example, we present a model for estimating nitrogen supply from chemical fertilizers within the crop production sector. As explained on the previous slide, nitrogen supply from chemical fertilizer is calculated as a product of nitrogen intensity, structural composition, and scale. Here, CA represents the cultivated area for a given crop. We apply the logarithmic mean Derbyshire index LMDI method to quantify how these factors changes over a given period. The Derbyshire index is an economic method used for factor decomposition analysis, and the key advantages of LMDI is that the calculations are simplified by using logarithms. This approach enables straightforward computation and evaluation using spreadsheet software such as Microsoft Excel. The analysis can be conducted using only statistical data, including unit nitrogen intensity and the cultivated area. The example results illustrate changes in the agriculture sector. For each crop, we evaluated changes over 3 periods. 2005 to 2010, 2010 to 2013, 2013 to 2019. The red circle symbols represent total nitrogen supply to groundwater. The positive values indicate an increase during the period, while negative values indicate a decrease. The contributing factors are color-coded as follows. Yellow for nitrogen intensity from compost or manure. Blue for nitrogen intensity from chemical fertilizers. Orange for structural factors. And green for scale factors. So for example, lettuce, at the case of lettuce, nitrogen supply decreased from 2010 to 2013 due to reductions in compost and fertilizers intensity, as well as a decline in the scale factor. Green is a scale factor. However, from 2013 to 2019, nitrogen supply increased like that, driven by increase in the structural factors. Structural factor is orange, and the nitrogen intensity of chemical fertilizer. So, yeah, for each crop we can read like that. The structural factor refers to the proportion of the lettuce cultivation area relative to the total cropped area. Through this type of analysis, it becomes possible to explore strategies such as shifting to crops that require lower nitrogen supply. Here is a breakdown integrated by sector. Overall, the contribution of the household sector is relatively small, like that. In the agriculture sector, crop production sector, nitrogen supply has declined in recent years, primarily due to scale factors. Green is scale factor. The livestock sector also experienced a decrease from 2010 to 2013 due to the scale factors. However, from 2013 to 2019, scale and structural factors offset each other, resulting in a little overall changes in nitrogen supply. Considering all three sectors together, nitrogen supply has shown declining trend in recent years, driven by both scale and structural factors. While this decline is desirable for the nitrogen contamination, the fact that it is mainly driven by scale factors suggesting reductions in the cropland area and livestock numbers, implying contraction in the agriculture and livestock production. Therefore, it is preferable to reduce nitrogen supply while simultaneously promoting sustainable agricultural development. As a more applied study, we have recently published the following research results. We analyzed agricultural statistical data from 10 administrative districts in the Kumamoto region. The Kumamoto is other prefecture, covering the period from 1960 to 2020, and clarified the spatial temporal dynamics of the nitrogen load and their driving factors. In this study, we developed a novel analytical framework that combines the LMDA decomposition method with a weighted tile index. Using this framework, we quantitatively decompose the changes in nitrogen load for both crops and livestock agriculture into three factors, the same as I explained. Nitrogen intensity, changes agriculture structure, and agriculture scale. The result shows that multiple external factors such as changes in agriculture policy, market fluctuations, and natural disasters. Actually, this Kumamoto region experienced a big earthquake 2016. Exert different influences on the nitrogen load. In addition, we identified 6 distinct development patterns across administrative districts and proposed concrete policy recommendations for nitrogen management strategies tailored to regional conditions. Okay, here I will present the current distribution of nitrate nitrogen groundwater along with the simulation results illustrating the effect of implementing agriculture and livestock countermeasures. Here, focusing on Shimabara city in the northern part of Peninsula, where nitrate nitrogen concentrations are particularly high area. We examined the progression of contamination using numerical modeling, as well as the effect of implementing countermeasures. Hydraulic conductivity was varied by several times between the surface and subsurface layers while maintaining the same order of magnitude. Since hydraulic conductivity generally decreases with depth, higher values were assigned to the surface layer and lower values to the subsurface layer. Spatial variations were also introduced between the mountainous side and the coastal areas, like that. The specific storage coefficient was set to 0.2. Groundwater recharge from precipitation was defined based on the long-term average precipitation. In order to reproduce typical groundwater flow conditions in the study area. Accordingly, recharge rates from the ground surface were set to 2.5 millimeter per day for paddy fields, agricultural land and forests, and 1.25 millimeter per day for urbanized areas. Based on the long-term average annual precipitation of 2,143 millimeter from 1976 to 2018. Rivers located at the northern and southern boundaries within the model domain were treated as discharge boundaries. These rivers for the discharge boundaries. The seaward boundary was defined as constant head boundary. This is the sea side. Constant head boundary at 0 meter above sea level, while all other boundaries were treated as impermeable. In modeling nitrate nitrogen transport, the nitrogen loading potential is first calculated at the ground surface, taking into account temporal variation patterns and based on statistical data. The nitrate load are then applied using prescribed reaching rate for agricultural land, livestock facilities, paddy fields, and other land use types. Dispersivity, a key parameter in solid transport modeling, is estimated based on the spatial scale of the system, geological system from upstream river livestock facilities, the pink areas, to the agricultural farm road network around here, where water supply wells are distributed along this road. Here is an example of the result. First, please look at the mid panel. The comparison between measured and simulated values shows that although simulated values were somewhat higher in some mountainous areas under steady state conditions, the overall agreement with the measurement is generally good, I think. The right panel shows the result for a scenario which the nitrogen load from farmland is reduced to 40% of the current level, and the nitrogen load from livestock facilities is also reduced to 40%. This is the case 40 to 40. Variations in nitrate nitrogen concentrations at the water supply wells W1, selected water supply wells W1, W4, W12. Largely conformed to the screen intervals. So suggesting that the progression of contamination has been reasonably reproduced, maybe. The countermeasure scenario is applied 2025 onward. At the site W1, concentrations appears to approach the standard values after approximately 50 years. In contrast, site W4 and W12 do not exhibit this trend, indicating that the standard may not be achieved even over a long period. To evaluate the effectiveness of countermeasures across all scenarios, we developed a simple evaluation index and plotted in its contour lines. Since this evaluation is layer specific, the contour lines are based on average values. Negative values indicate that future concentrations will exceed current levels. Higher values represent better performance, although the interpretation depends on the evaluation point. As expected, the case 80 to 80 scenario represents the most effective countermeasure in the simulation cases. This analysis results reveals that sensitivity to the livestock treated related to measure is relatively low. Horizontal axis is the livestock measures, and the vertical axis is the cropland agriculture field measures, countermeasures. So implementing agricultural countermeasures requires the appropriate application of fertilizers. So therefore, conducting soil diagnostics as needed, such as assessing available nitrogen, and strictly managing fertilizer application rate are considered effective strategies. We aim to communicate these findings clearly and apply them to environmental policy in this region. So now I would like to summarize today's presentation. Locations with high nitrate nitrogen concentration are concentrated in the northern part of the peninsula, with particularly soil pollution in Shimabara city in the northeast. Meanwhile, the northwestern region is considered to contribute to the deterioration of water quality in the reclamation reservoir. Analysis using sterols appears capable of distinguishing sources derived from human and livestock waste from those originating from chemical fertilizers. Factor decomposition using the LMDA method enables detailed analysis of pollution sources and help identify priority areas for countermeasures. Simulations of countermeasure effectiveness for nitrate pollution in the Northern Peninsula reveals high sensitivity to agricultural land measures. Conducting soil diagnostics to assess available nitrogen levels in farmland and strictly managing fertilizer application rate are considered essential. Okay, that's all. Thank you very much.
Thank you very much, Professor, for very informative lecture on nitrate and nitrogen contamination in the groundwater system in Japan. So now platform is open for the question answer. If anybody have any question, please write in the section of question and answer. So we will take your questions. So there is one question, Professor, from Johnson.
Yes.
Are there any seasonal pattern on your nitrate pollution? Are there any seasonal pattern on your nitrate pollution?
Yes. Actually, in the rainy season, groundwater levels become higher, and then the nitrate concentration decreasing. So maybe the dilution effect is affected on the concentration of nitrate concentrations. But later, becoming increasing the concentration after the rainy season, something like that.
Thank you, Professor. And there is one another question from Valentina. She's asking, can you show us again the paper of the last study?
Last study?
Yeah.
Yeah.
This one.
Okay.
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 Yeah. So there is another question from Hadi. So he's asking, how did you set the solute transport parameters? Question mark. And what is the straightforward procedure for setting the solute transport parameters?
Parameters for solute transport parameters.
Yeah.
Some dispersibility. Nitrogen load was adding from the surface with the we have statistical data of agriculture. なんだろうな。We have data for every locations. How many crops, areas of the crops and the crop type or something like that. We have the census data, agriculture census data. Based on that statistical data, we estimated reaching rate and なんだろうかな。Actually, prefecture recommended fertilizing concentration of nitrate for each crops. So we just summarize for this crop, how many loading we calculated for each locations. And also, we have a data of the livestock farmers and livestock numbers of the animals. So yeah, we have intensity of nitrate intensity for each one animal. So we can calculate also. Then applied for the from the surface the input of the nitrate concentrations, but also used for the leaching rate for depending on the land use. But in this case, just two types of land use. Only urbanization or other natural land or something like that. Only the dispositive is like that.
Have you, Professor, also considered the hydrogeological parameters for the numerical modeling?
Like hydraulic conductivity, right?
Yeah.
That? なんかね、actually, this, yes, we have running several times for decide the distribution of the hydraulic conductivities, but we would like to more, but simplified the distribution. So we just 4 areas, like divided into 4 areas like that. And the best fit parameters I decided and then used to the simulations.
Thank you. So there are a couple questions more, and I'm going to read for you. So one again question is how can sustainable agriculture management be practically done to minimize the nitrate contamination in the future? This is a question from Jason.
It's a difficult question, but maybe based on this kind of analysis, we can find the best crop patterns for that area or specific areas. So maybe we can shift the crop changes, the low intensity products, or also the livestock is also changes. Maybe, yeah, something like that. So we don't want to reduce the number of the livestock or reduce the crop production, but we try to protect the environment. So maybe we can find something based on this analysis.
Thank you, Professor. There is another question from Arif. It is regarding to how differentiate the concentration of the nitrogen pollution in deep well and shallow well in your research. So it's asking there is any significant difference on the type of deep well and shallow wells on the groundwater based on your research.
Okay. Yeah, actually, actually, we don't have exact data for the deep and shallow, but actually how many depths of the wells we don't know. But we have only the data. This well is shallow well, or this well is deep well, or something like that. And deep well is recently recovery. どっちだったかな？No. Shallow well is recently recovery from the nitrate concentrations, but deep well is still contaminated. So maybe deep well is old water, infiltrated water. So maybe it's more time to recovery or from the contamination. I think so. That somewhat like that differences.
Thank you, Professor. There is another question from Shiraz and asking about how applicable is this methodology combining sterol analysis and the LMDI method to other drainage basins with different geological or land use settings.
なんか、difficult. Combine these all method to...
Combining this sterol analysis with LMDI method for
Okay.
different basin and different geological setting or different land use pattern.
Yeah. Yeah, actually, this method is not depending on the geology, maybe on the not to depend on the geology or the different geology or something like that, because only the detection of the sterol concentration in the water, or it's also analyze the soils. But so maybe, yeah, it's easy to apply to other regions, other geologies or something like that. LMDI is only the which one かな? Only uses the data, so not limited to the locations or something like that. If you have statistical data of the areas and the intensities, only that we can calculate.
So thank you, Professor, for answering this question. I have one more question from
Yes.
Please, can you share your PowerPoint at the end? So I'd like to inform you all. This is a video is recorded for this presentation and is going to be shared with the IAH. So he's asking about your presentation, whether you're going to share your PPT with the participants or not.
You are asking, can I distribute this slide?
Yeah.
Yes, of course.
Okay. So Professor will share in the PDF form. If anybody needs this presentation, please contact to me. So there is another question from Dr. Chinmay, and he's asking, what is the residence time of sterol in different reservoirs?
Residence time of sterol?
Yeah.
Residence time, I'm not sure. I'm not sure. ステロールは、そうね。I'm not sure. Just, I don't know. Maybe we believe the sterol is なんていうのかな、ステーブルかな。
And he asking another question. Reservoir means in lake, river water, groundwater. So what does mean of reservoirs? Like mean in lake, river water, or groundwater?
What's river water, groundwater? What?
Yeah.
What's the question?
He's asking the residence time in different reservoirs. So like in lake water, in river water, in groundwater. So is there any idea or some experience on this residence time?
Yeah, actually, I'm not sure about the residence time, but river water concentration is higher in the river water, but most of them are absorbed on the riverbed or sediment, and then groundwater concentration in the groundwater is very low concentrations, but we can detect both. So yeah, well, we have that experience, only that.
Okay, thank you. So we have little more time. If there is another question, we can take one more questions from the audience. Okay. Okay. So there seems no questions, Professor. You have answered all the questions.
Okay, thank you.
So, there is one question. Just I will take 1 more minute. Yours. And the question is: Are there any special pattern in contamination, that is more contamination downstream? Jason is asking this question. Are there any special pattern in contamination, that is more contamination downstream?
Downstream?
Have you seen any pattern of the contamination moving the content from upstream to the downstream, or some observation?
Okay. Yeah, we have we have another publications related to the upstream concentration changes upstream to the downstream, but no. Yeah, actually, we expected that we estimated the pollution sources are on the upper region of the mountainside. Actually, the smells of the livestock farmers, so they moved up to the mountainside and then they formed 何ですかね、livestock village like that. So they concentrated pollution sources on that side, and then pollution spread to the downstream like that. So the most contaminated areas are the more upstream areas like that.
Okay. Thank you, Professor. So probably we can close to the end of this session. So I would like to take this opportunity on behalf of the Early Career Hydrogeologists Network, IEH. I would like to thank you for your brief presentation about the current situation of nitrate in 3 cities of Japan, covering about the source identification, groundwater geochemistry, and this lecture also gives the information on numerical modeling and different kind of sources of nitrate pollution. So thank you so much on behalf of the ECHN IEH to accepting our invitation, giving these lectures. And I would also like to thanks to the IEH members and also ECHN IEH members and committee members for their always support and contribution. And I would like to all the participants, thank you for the joining. And I'd like to inform you that if anybody interested in young researcher to look the Early Career Hydrogeologists Network, please visit our website. It's like you can type Early Career Hydrogeologists Network of IH. You can see our work, and we are working to educate and aware and develop networking with the young researchers. I would like to invite all the young researchers, please join us. And I'd like to thanks to the team of the IH for all the support. So thank you, Professor. Again, thank you so much. Thank you, everyone, for joining. And hoping in the future we have other interactive sessions.
Okay, thank you very much.
Thank you. Thank you, everyone.
Okay.
Namaste.
Okay, thank you very much. Namaste. ありがとうございます。Thank you very much.
Thank you. Thanks.
Okay.